Hello everyone. I hope I'm audible. If not, please let me know. So last time we left with frequency response analysis, and this Wednesday today we will complete the Nyquist and Bode, that is both frequency response analysis techniques. These are two different plots that serves two different purposes. It's an analysis tool. It's not like a control mechanism. It's just an analysis tool to see how well your system is behaving and what is the characteristics of your system. We based on this analysis and by understanding the nature of that system, we will develop control in later stages. Okay, don't think this as a control technique. This is one of the tool that we use in our control systems. Right. Today we want to cover both types of plots. I want to start with the Nyquist plot first. Last time we have been discussing about the stability criterion. Some of you have difficulties in understanding that. So first we will see how to design a Nyquist plot or how to draw a Nyquist plot from a transfer function, and then we'll try to understand the point of stability criterion from there. I think it will be more easy than the way we already approached. Okay, fine. Nyquist plot can also be called as polar plot. It doesn't have this kind of XY plot. Instead, it deals with degrees 0 degree, 90 degree, 180, 270 kind of. So, first thing, I want to coin the notation I used to use. I will use always this as a 0 degree. This is 90, 270, 360, sorry, 180, 180, 180, 270. This is again 360. 0 or 360, I will use interchangeably. On the other hand, this is like a anti-clockwise direction, positive side. Okay. This I called as positive angle. I will use counterclockwise hereafter, not any anti-clockwise. Okay. Even though if I said something by mistake, anti-clockwise by mistake, understand that as a counterclockwise. Okay, both are same. And next thing is negative angle. If we consider this as a negative angle, that is clockwise direction. This is counterclockwise direction. So this will become, this is 90 minus 180 or same. And this will be minus 270. Okay. So this is a negative angle. Both means the same. If I say 90 or minus 270, it means this direction, top direction. If I say 270 or minus 90, both represents the bottom. This can be both 180 or minus 180 based on the way you approach the system. Okay. This is 0 or 360, right? Remains always 0 or 360. Note down somewhere. It will be helpful for our problem solving session. Okay. Right. Now, we already saw an open loop transfer function can be represented as only g of s, but a closed loop transfer function will be represented as g of s divided by 1 plus g of s into h of s, where this below we call loop transfer function. And also we use this to find the poles of any system. So we equate this and we call this as a characteristic equation. We are very familiar with this concepts. Also, you would have done this in RH criteria, right? In week 6 or something. Okay, so if you are in taking this as a denominator, that helps us find the stability of any system. Fine. So from here, in the frequency response criteria, or when taking the frequency response introduction, I told you how to find a magnitude of any system and phase of any system. So magnitude of m of j omega will be represented using the root of b square plus a square, where m of j omega is equal to a plus bj, if it is a complex number. So a phase of m of j omega would be tan inverse of b by a. Okay. For a numerator, if it is in the denominator, it would be minus tan inverse of B by. Fine. So there are two other things that you need to remember before going inside. That is minimum phase system and non-minimum phase system. For a non-minimum phase system, the zero, that is a numerator of any transfer function, will lie in the right half of the S-plane, that is unstable region. For minimum phase system, the zero of any transfer function would lie in the LHS of any system. It would be in the stable region. For a minimum phase transfer function, that is with zero, lies in the left half of the S-plane with only poles, and the type number of the system determines the quadrant at which this polar plot starts, and the order of the system determines the where the quadrants at which the polar plots ends. For example, I will write this for any minimum phase system. Why it is minimum phase? Because we don't want our zero to be in the right half of this plane. I want both poles and zeros to be in the left half of this plane. So I'm designing for any minimum phase system, this would apply. Okay. Type number determines the start of the start quadrant of the polar plot. Order determines the end quadrant of the polar plot. This I'm telling you, polar plot, Nyquist plot, both are same. This I'm telling you to help you how to understand, how to draw the Nyquist plot. The change.
Excuse me, ma'am.
Yeah.
What is the start
Yeah,
quadrant?
I'm going to explain it now, right now. You will understand in next 5 minutes. I will write it, and when I draw it, you will understand. Okay, so give me a minute. Okay, fine. Remember this one and the above one here. So I'm going to tell a basic rule to start and end, or to draw the polar Nyquist plot. Okay, I will stick to the Nyquist plot to avoid confusion. So now, if I want to draw a Nyquist plot for a system like this, S plus A, where S plus A is a pole, where pole lies in the minus A. Maybe S plus B by S plus A. That is, this is your zero, this is your pole. We all are clear with this, right? So they are saying the change in the shape of your Nyquist plot can be predicted due to the addition of a pole or a zero. If I am given with a Nyquist plot and there is a change, and I can say with the change whether I have added a pole to a system or a zero to the system. For that, you should know how to draw the Nyquist plot in the first place, right? That is the uh, concept here. So when I add a pole, when we start with a pole to the system, the polar plot, the Nyquist plot endpoint will shift by minus 90 degree. So for a zero, then this will be shift by plus 90 degree. So before I have introduced you to how I am going to use these denominations, right? How 0, 90, 180, 270. I will start with this. So if this is 0, this is positive 90, 180, 270, right? So if you're, according to this, the type number determines the start of the Nyquist plot. So if I want to start my Nyquist plot, I would look for the type of my system. What is type? Type determines how many poles you have at the origin, right? power of s, that is your type. If this means this is s power 0. If it is type 0 system, your Nyquist plot will start from here, type 0. For a type 1 system, it will start from here. For a type 2 system, it starts here. For a type 3 system, it starts here. So this is how you start drawing your Nyquist plot for any transfer function. For starting point, you will look for the type. Start type. For end point, you look for the order of the system. My order for this example system, it is 1, right? So how to end it is, this is where it will end for a type, sorry, order, right? Order 1 system. This end for order 2. This is for order 3. This is for order 4. Fine. So based on this degrees, this will be equated by the magnitude and phase criteria later. So when we have an example, you will understand. For example, if I give this, um, it is a minimum phase system. To understand it is a minimum phase system, 0 lies in the left half of the S plane. So I'm giving S into S plus 2. So for this system, from the above diagram, can you tell where the start point will be? To start, you should look for the type of the system, type number of the system. So how will you, can you tell me what is the type of the system?
It's type 1.
Type 1. Then if it is type 1, it will start from 270 degree or minus 90 degree, anything, any one of this, right? Whether, what is the order of the system?
First order.
First,
Second order.
it's a second order system. So your polar plot or the Nyquist plot start from here and end somewhere like this. Now you understood? This is how we draw a Nyquist plot. Exactly how we are going to draw that I will explain later. But for a context, how your Nyquist plot looks like can be determined from your type and order of the system. Any doubt in this? So for a type 2 order 3 system, how it will be? For a type 2, from where it will start? Your
Left
Nyquist
side.
plot? From 180 degree.
Yes.
For order 3, where it will end? Which quadrant? If this is 1, 2, 3, and
Second
4,
quadrant.
it will end at second quadrant. Something like this, your Nyquist plot will come. So your Nyquist plot arrow will be like this. Okay, fine. Now we know some idea about how to how a Nyquist plot will start and how it will end. Now we will see for each and every orders and each and every transfer function notation. Okay. The first thing is I would like to start with a simple system that is type 0 order 1, maybe something like this. No type, only order 1, first order system. For this kind of system, I will rewrite this as a 1 by how will you write 1 by as plus 1, right? We always write this as a 1 plus tau is, where tau is a time constant format, right? So it will be 1 by 1 plus 1 by a into s. The same system has been rewritten as this. Okay. So now your system g of j omega, if g of s is equal to 1 by, I will give,
Ma'am, if we write 1 by AS,
ah,
then there will be above there will be 1 by AL.
it will be there. Yeah. If I take 1 by a is common, it will be there. Yeah, that's right. It's not 1 by a, correct. It will be there, but for common system, I'm saying, let us consider that 1 by a above everything is equalized, and I have a system represented as a 1 by s plus 1 by 1 plus st, where t is a tau constant, time constant. Okay. So
Okay, ma'am.
for a frequency response for a Nyquist criterion, I would do replace all the s with the j omega, right? So in this case, I would replace this with j omega t. Now you find this magnitude and the phase for the same system. So if I write this in terms of magnitude form, how it will be? For a plus bj, it will be root of a square plus b square, right? So for this would be uh, root of 1 square plus omega square t square. Is it right? So this is the magnitude of my transfer
It will
function.
be 1 by 1 plus omega square t square.
1 by, yeah, it's right. Yeah. Overall, if I take a magnitude like this, it will be right. 1 by, I will write it properly. 1 root of 1 square plus omega square t square. Right. For phase, how will you write? So if you have something like this a plus bj, it will be tan inverse of b by a. But if it is 1 by a plus bj, it will be minus tan inverse of b by a, right? So for here, it will be minus tan inverse of omega t by 1. So overall, I can write this as a 1 by 1, sorry, 1 square plus omega square t square minus tan inverse of omega t. Is it right? It will be this angle. This is the magnitude, whereas that is the angle. Fine. Now you approximately draw the Nyquist plot
Ma'am,
one.
J omega we have to write with magnitude and angle.
G of j omega, we have to write what?
With magnitude and angle.
With a magnitude and angle. You have to first find the magnitude and phase angle of the system before drawing this Nyquist plot.
Okay.
Once you find this, then only you will calculate at what point of omega the Nyquist plot will change from where to where. Okay, from the rough diagram, you know how where the starting point and ending point, right? So if it is 0, 90, 180, 270, this is a type 0 first order system. Then you tell me where it will start and which from which degree it will start and from which quadrant it will end for type 0 order 1. Can you recollect it without seeing that first?
It will
Ma'am,
start
from
from
0 degree.
0 degree and end at 4th quadrant.
Starts from
0 degree.
0 degree. Okay.
End
Somebody else
at
tell where it will end.
4th quadrant.
In
It will end at fourth quadrant.
first.
First order. Correct. So you will get something like this roughly, right? But properly, what will be its magnitude that we are going to find? Roughly, it will start from 0 and it ends with fourth quadrant. That we know. Okay, fine. Now we calculated formally. What we used to do is we will approximate from the starting point to the ending point. We don't really calculate for each and every instance. We will see as omega tends to 0. That is the starting point, right? Minimum value. How the system would be or at which point it will start. And then we will measure as omega tends to infinity. That is the ending point where it will really reach the point. This is how we calculate the Nyquist plot criteria. So from here, if you my g of j omega as omega tends to 0, how it will be? Minus tan inverse of 0. What is tan inverse of 0?
0 degree.
0 degree. Fine. Angle at which my omega tends to infinity minus tan inverse of infinity. You can use calculators
5.
also. It will be minus 90. Tan infinity 90, as it is minus tan infinity, it's minus 90. Similarly, if I calculate the magnitude, what if I put omega equal to 0? 1 by root of 1 plus 0. 1, same magnitude when omega tends to infinity. How it will be? 1 by 1 plus infinity. 1 by infinity is again 0, right? So from this, how can I approximate this? When omega is equal to 0, my magnitude is 1 at an angle of 0 degree. When omega tends to infinity, my magnitude is 0 at an angle of minus 90 degree. So where is minus 90 degree? Here. This is minus 90 degree. That's why I put both notation. 90 and 270 both are same. So here at 0 degree, I'm starting with a value of 1. My magnitude is 1 here at 0 degree phase angle. That is the starting point, and it is ending at 0 at a minus 90 degree. This is minus 90 degree, right? So this is my Nyquist law for this transfer function. Is it clear? For a transfer function of type 0 order 1. So that's what we saw here in a shortened notation. But technically, this is the reason behind it. If you calculate the magnitude and phase angle for it, it will exactly give you the same. It starts at 0 degree and ends at fourth quadrant. That is your minus 90 above. It lies in the fourth quadrant. Clear? We will do for one more thing to understand it better. Then you can do it for yourself by for all the type and all the order combination. So if it is type 1, order 2. So how it will look like? Something like this. Can I write something like this? S into 1 plus ST. You will be given with the question like in this format only. 1 by ST only. Okay. Now what I will do? I will replace S with j omega. 1 by j omega. 1 plus j omega t. So the first thing I would do is I would calculate the magnitude for this. Okay. This is in the other format, right? I can do like that, okay? So you don't need to multiply and divide. For now, I am keeping as it is. So this will be j omega plus j squared omega square t. So it will be minus 1 omega square t or minus omega square t. The real part is minus omega square t plus j omega. Only j omega, no t here, right? So for this system, how will I write? Magnitude would be 1 by root of omega square plus omega square t the whole square. Would be good, right? Fine. Now root of omega square plus omega power 4 t square. I can write this as omega into root of omega 1 plus omega square t square, right? So this is the magnitude of my system. For phase angle, how to write a phase angle for this? Considering this as a final shortened form of this, it would be minus tan inverse of b by a, where is b? Omega by minus omega square t. So this will become minus t inverse of 1 by omega t, right? Or we don't have to write like this, right? So wait, there is a shorter notation, so you can straight away write this as for omega it will be 90 degree as it is minus 90 minus of tan inverse of omega t by 1. Right, 1 omega has taken outside, so it is omega t by 1. So the overall your angle would be minus tan inverse of omega t. Fine. Now my magnitude is 1 by omega root of 1 plus omega square t square. My angle is g of j omega equal to minus 90 minus tan inverse of omega t. Now, when omega equal to 0, how my magnitude would be 0, anything by 0, infinity. My angle would be,
Ma'am,
yeah,
uh, can you explain how you write minus 90 minus tan inverse omega t by 1?
for a omega representation like this, we can straight away write minus 90 degree it would be, because it is a orthogonal component to your plane, right? So when you find an angle for 1 by omega, it will be minus 90 actually. For omega, it is 90. Since it is 1 by omega, it is minus 90 degree. For this, I have calculated like tan inverse of b by a. That's it. Still not clear?
Ma'am, ma'am, you are writing from g omega, g j omega from main equation.
Oh, for from here also you can assume the same thing. Both are same. I just wrote it in a shortened form.
Okay. I understood. Ma'am.
Yeah, okay, fine. Now, from here, I think it's clear. So, if I substitute 0 in this, 1 by 0, 1 by 0 infinity. If I substitute 0 here, tan inverse of 0, 0, minus 90 degrees the angle. When omega tends to infinity, my magnitude become 1 by infinity 0. Angle would be um, tan inverse of infinity 90 minus 90 minus 90 minus 180 degree, right? So, when omega tends to 0, it starts with infinity at an angle of minus 90. When omega tends to infinity, it's come down to 0 at an angle of minus 180 degree. So if I write it 0, 90, 180, 270, minus 90, minus 180, minus 270, then it starts at infinity at an angle of minus 90. So from here, somewhere in the infinity, okay? And it starts from here, so the arrow would be like this, and it ends in here. So I will write in this direction. So it will be easy. It ends in third quadrant. Mine from infinity, it ends somewhere here at 0 at minus 180 degree third quadrant. For this is a type 1 order 2 system. So if I look here, for type 1, it starts with here, and for order 2, it's in third quadrant. Both are same, right? So we got the same thing at, at an approximate level. Right. I hope you are clear with this. If you have asked some question based on this, you will be able to answer this, I
Can
guess.
you explain a bit, man, that graph you drawn?
Which part you want me to explain?
From minus 90, how it comes from infinity?
For minus 90, how it comes to. Okay. See, I can start anywhere here, right? From my infinity means I can start anywhere here. It can be minus plus. We don't know. That's been known using this in quadrant, right? So if it is ending in the third quadrant, so I'm starting from here, and I'm going to somehow like this. So it is like a approximate value only. You don't know anything in between. For no, we don't need it. We just need to know where how it is encircling and where it is encircling. So for that, this approximation is enough. Since it is minus 180, it's going to happen here in the third quadrant, and it is reaching 0 via the third quadrant. So that's how I drew this line. Is it clear? From infinity at minus 90 degree, it goes to 0 at minus 180 degree. So it covers the third quadrant. That's it. Clear? Whoever asked this question?
Yeah.
Okay. 0 at minus 180 degree. Fine. Now, you might expect some question like this, that I would have given the transfer function like this, a square into s plus a. So maybe not S plus A, 1 by some ST. Okay, and I would have given some four options for you to choose like this, and you have to choose the proper Nyquist plot for this. This could be a question. Okay, prepare for this. Please rewatch this recorded session and practice something by you. Fine. Um, Similarly, practice this type 0 order 2 system. So you would see something like this. So far we have been seeing in the same quadrant, right? But for this kind of system, you would see something like this. It would starts at 0 degree at 1, and it can go till the third quadrant to go to infinity. Sorry, 0 at minus 180 degree. So it would be for the system, this will be like this. As omega equal to 0, omega equal to infinity, it would be 0 at minus 180 degree. So you might need to cross from one quadrant to another quadrant to go from here to there. It can also be written like this, whatever way. But since we know only the initial and final point, you can visualize this accordingly. Fine. And before moving towards this, there is a very big topic, that is what is gain margin and what is phase margin. These are two very important topics in the frequency domain characteristics. So for Bode plots also you would need this. In general, how we define a gain margin is that this is the inverse of magnitude of g of j omega, whatever your transfer function, at phase crossover frequency. The phase crossover frequency in turns, I told that the inverse of your magnitude at phase crossover frequency. What is phase crossover frequency? It is the frequency at which the phase of g of j omega, otherwise I will write like this, the phase of g of j omega is equal to 180 degree. So for example, it will be easy to represent using a Bode plot. We are going to see what is Bode plot. Okay, for now I am explaining this. Usually Bode plots consist of two things. One is magnitude plot, other one is a phase plot. Similar to Nyquist, we will do this also. We will first calculate magnitude and phase for a transfer function to find the Bode plot also. That these initial steps are same for both plots. How we draw the plots is a different thing. Now, phase crossover frequency is frequency at which the phase angle reaches minus 180 degree. Okay, fine. So this is your omega, right? So if this is my phase plot, for example, and this is my okay, if this is my phase plot, okay, so the frequency point at which my phase angle, that is phase of j omega, reaches exactly at minus 180 degree. This frequency is called as phase crossover frequency, or it is omega pc. Any doubt in this? What is phase crossover frequency? Can you visualize this? The frequency at which your phase angle reaches 180 degree, that is minus 180 degree in Bode plot. Any doubt in this? Okay. Your gain margin is, this is your gain margin, at which the same frequency, inverse of your magnitude will be your gain margin. So your gain margin is equal to 1 by g of j omega at omega equal to phase crossover frequency. I hope this is clear. If it is confusing, please ask me. Let us clear this out here itself. Your gain margin is equal to inverse of your magnitude at omega, where omega is the phase crossover frequency.
So, ma'am, first we have to find phase crossover frequency.
To
Then we
find
have,
the gain margin. Yeah,
yes, ma'am.
correct. Then comes the phase margin. Phase margin is defined as it's defined in a formula. It's added to 180 degree added to your phase angle of the j omega gain crossover. Okay, this really it's going to be confusing. See, first learn this stuff. Okay, this is always we represent frequency using omega, right? So omega pc represents frequency. Omega pc means phase pc, phase crossover frequency, and omega gc is gain crossover frequency. So if I want to use this, you need to know what it is. If I say this pi of PC, then it is angle or phase angle at phase crossover frequency. If I say GC, this is phase angle at gain crossover frequency. Any doubt in this? We know phase crossover. I am going to tell what is gain crossover. No need to worry about it. First, you understood this notation, right? If nobody asks any question, I am assuming
It
that
is
you.
gamma or something.
It's phi. We call this phi. I
Ma'am,
will tell.
What it is?
Okay. I will tell. That is phase margin. That's it. We defined it like that, no? You understood these four, right? That's what my question right now.
ma'am,
Ah,
you have told that phase crossover frequency we find at minus 180 degree when the magnitude will go to the minus 180 degree.
uh-huh. Yeah.
Then what about phase angle at the phase cross frequency? Mm,
Same. No, it's same. Whatever it is, just for the notation, I'm saying.
okay.
If I put this represents phase angle. That's it. You are going to see only the phase angle at gain crossover frequency.
Okay, ma'am. Okay.
What
Phase
is
angle
grain
at
gain?
what?
What is grain crossover frequency?
That I will define. So gain crossover frequency is that I am going to call it as omega GC. Gain crossover frequency is frequency at which the magnitude G of j omega is equal to 1. Here, it is 1. So, if this is your Bode plot, this is phase, this is magnitude, this is, I know this is confusing, this is phase. So, your phase crossover frequency, your plot is like this, okay? And your plot is like this, for example, I'm saying. Okay, now there are two things happening here. One is this is minus 180, this is 0 for now. Your Bode plot will be in decibels. I will come to the point later, but for now, take this as 0. How do we design the phase crossover frequency? Whenever your phase plot reaches minus 180, that's where the phase crossover frequency happens. For gain crossover frequency, whenever your plot reaches 1, gain equal to 1. So the same frequency is called as gain crossover frequency. Clear? So phase crossover frequency is phase angle G of j omega equal to 180 or minus 180. Both are same. Okay. Gain crossover frequency is your magnitude is equal to 1. Any doubt? Fine.
Earlier you told that this G of j omega angle will be 180. After that only it will.
180 minus 180 both are same. No, here where is that?
Okay, okay.
Ayo, the other thing, whatever I wrote, it's gone. No? Uh, Here, right? Both are same, right? So that doesn't matter. Informally, it was defined as 180 degree. That's it. But angle wise, both are same. Minus 180, 180, both are occurs at the left of 10 seconds. Fine. Now the additional terms phi we have discussed here, no? So the phase angle, and this is where the gain happening at gain equal to 1. The frequency at which the gain becomes 1 is gain crossover frequency. Phase angle becomes this. This is the phase angle phi at gain crossover frequency. Clear? This is phase angle at phase crossover frequency. Both are same. Minus 180. Always it will be minus 180. Clear? So your important term here is gain crossover frequency. Sorry, phase angle at gain crossover frequency. That is the phase angle whenever the your j omega g of j omega equal to 1. So that's what I have given here. So this is the one I explained now. If you added 180 degree to that, then it becomes phase margin. Please let me know if you don't understand it.
What that notation called?
There are many things at a time, right?
That phase margin.
Gamma is a representation for a phase margin. Just a
Gamma.
very
That is gamma, right?
yeah, gamma, gamma.
Okay.
Fine. When we plot Bode plot, we will see how to find it from the graph. Okay. Um, Clear.
Maybe scroll a bit.
From here.
Uh,
Okay. Um, Let me see if I can solve some problem.
Ma'am,
Sorry, there is some network issue from my side.
Ma'am,
Yeah.
ma'am, can you do week 7 question number 6? That is about phase margin, gain margin
Okay.
question.
I will do 1 minute. Give me a minute. I will explain this and I'll do it last. Okay, my screen is visible, I think. Let me write. I don't know how to increase this font size. Okay, right. Now we'll see this. This is how I want to write this transfer function, that is minus a square minus 4s minus 6 divided by a square plus 5s plus 4. This is going to be my transfer function. I'm going to write it in the format of a MATLAB. So how can I write it is, I can write it as numerator and denominator representation, that is minus 1, minus 4, minus 6, coefficients of all the numerators. D and denominator variable going to store coefficients of all my denominator, right? That is 1, 5, 4. Now I'm going to plot a Nyquist plot for this transfer function, numerator comma denominator. This is how you can give. This is one of the method to plot the Nyquist out of the transfer function. You can do it from transfer function representation also. If you see here, can you see this diagram? Nyquist plot here, right?
Yes, ma'am.
Fine. For this kind of system, this is a Nyquist plot that we can also draw this using hand. This is a kind of type order 2 system, type 0 order 2 system. Okay. It starts from minus 0 degree and ends up into minus 180 degree somehow, somewhere it is 1 to 0. So, so this is a Nyquist plot of this system. Now from here, you can see that it has two encirclements in a clockwise direction. For example, it starts from here. Okay, it starts from here and it goes like this, and again it takes another turn and comes and ends here at 0 degree. Fine. So this is a clockwise direction. This is how we used to find the stability criterion of the Nyquist. So how we saw the Nyquist stability criterion
Ma'am,
last time.
how do you say it is two
So there is a cross, no? So there are two circles. One circle is this, another circle is big one. Here there is a cross, right? It cross its path.
okay.
It comes back to the same path, right? I will show you, explain you from that microstability problem book itself. Fine. One minute. This is a Norman and Nice book. So I'm using this to explain this from here. So if it says that you can see this like this. See, if there is no encirclement of -1 plus j point, we saw this stability criterion formula last time, right? It is n equal to z minus p. So the beauty of this Nyquist plot in the sense, first for the first part of this session, we learned how to draw a Nyquist plot. The second part, now I am going to cover how to find the stability of any system using this Nyquist plots. Once we draw this Nyquist plot for any system, from that, we will be able to tell the closed loop system is stable or not only from the plot or from the open loop poles and zeros. So if you have a G of S for your system, just write it in terms of 1 plus G of S into H of S. For the G of S into H of S, you will draw a Nyquist plot from where it starts from 0, omega equal to 0, omega equal to infinity. You know the starting and ending point and which quadrant it is going to cross. So from that, you will know how many times that it is going to cross the -1 plus J0, right? So using that, we are going to find the stability. If there is no, in the first point, if you see, if there is no encirclement of -1 plus J0, this implies that the system is stable if there are no poles in the G of S in the right half of the sphere. It states, see, for my system, if you see s square plus 5s plus 4, this is the denominator, right? I'm going to find the pole of this denominator, that is s square. How can I find the pole of the system? This is equal to E of S pole of s square plus 5 into s plus 4. Or pole of maybe. I don't remember how to find suit. Okay, I need to do it as a transfer function, right? Num comma denominator. Equal to. Okay, fine. This is my transfer function. Now I can find pole. The pole located at -4 and -1. So both are at the LHS, that is stable pole. This is an open loop system. Okay, this is my open loop transfer function G of S, where the poles lies in the -4 and -1. That is stable. There is no open loop pole. So the first thing the criteria says, where it is. The criteria says this implies that the system is stable if there are no poles in the right half of this plane. In our case, for our example, there are no poles in the right half of this plane. Otherwise, there is no encirclement here. Did you see any encirclement around the -1 here? It is not encircling -1, but it is going through -1. -1 is here, wherever I am keeping my cursor. So it is not encircling.
Ma'am, what do you mean by encirclement? I can't understand this.
Okay, fine. Let me go back to my screen and explain. See, if this is my -1 plus J0, right? So why we are particularly focusing on -1, that is another story for that, because our loop transfer function is 1 plus GH. If we found a Nyquist plot for GH, then it will become -1. That's why we are looking for -1. This is one thing, important point. Another thing is the stability, Nyquist stability criterions tells that your system, where it is. N equal to Z minus P, where N is the number of counterclockwise encirclement around minus 1 plus J0. Z is the open loop poles and P is the open loop 0. So the idea is you have only open loop transfer function. With this open loop transfer function, I am going to say whether your closed loop transfer function G by 1 plus GH is stable or not using the Nyquist plot. That's what our idea is. So only we have an idea about GH, its open loop poles and zeros. For example, S plus A by S plus B. This is open loop 0, this is open loop pole. And I'm going to do a Nyquist plot and see whether it is encircling minus 1. Encirclement in the sense is it rotating? Encirclement is just a rotation around this point. Either it is a clockwise or anti-clockwise direction. With that direction of rotation around the minus 1 plus J0, I am going to say whether my closed loop system is stable or not. So the Nyquist stability criterion says your open loop zeros minus your open loop poles should be equal to the number of counterclockwise encirclement around your minus 1. So if I encircle this one time, then my Z minus P should also be equal to 1. Then my system is stable. If this is not matching, your system is closed loop system is unstable. That's what the criterion says. It's a very powerful criterion. For example, if I encircle my minus 1 2 times. So this is also counterclockwise. This is also counterclockwise 2 times. But is it my open loop pole 0 minus open loop pole is equal to 1. This is 2, but this is 1. Then my system is closed loop system is unstable. Is it clear? Any doubt in this?
No, ma'am. Now it is clear.
Fine. So this is what this particular formula tells you. So from your Nyquist plot, first you will see how many times your plot encircles your minus 1 and in which direction. That should be counterclockwise, not clockwise, right? So if it is clockwise, you have to consider it in the negative value. For example, if I encircle 1 in one direction like this, then it will be n equal to minus 1 here, not 1. If it is like this one time, then it is n is equal to 1. So now you find how many poles are in the left half of this plane and how many open loop zeros are in the left half of this plane. If you minus these two, then it should be equal to your encirclement in counterclockwise direction of your Nyquist. That's what your stability criterion says. I hope this is clear now. And now I'm stopping here. For those who want to join to next classes, I will continue with Bode plot here. If you can't attend this live session, please attend please rewatch this video from the recorded session. Okay. Because I want to take some more time. Some people might not have that time. So you can feel free to leave now and watch this session for Bode plots. Okay. Before, like my screen, this one is visible. Huh? Okay. My laptop screen is not visible. Okay, no problem. Let me do it from here. Now we will resume to Bode plot. This is another frequency response analysis plot. So one of the biggest difference between Nyquist and Bode is that Bode can be represented in two different types of plots. One is it's not both together. 0 at an angle of this. It is a separate plot of magnitude and phase. So if you want one, you can plot only one, then both. Then need to know both. And also you can plot it together, and each and every point in the Bode plot can also be calculated rather than in the than we do in Nyquist plot. This is more defined one than that, and this is in a logarithmic scale. That is much bigger difference from the Nyquist plot. If you want to use it for a higher dimensional system, Bode is more convenient than the Nyquist plot. That's why we used to choose Bode more than the Nyquist plot. Nyquist is more towards stability. Bode is more towards the analysis or the time domain specifications of your system, overshoot and under values and everything. So both are different types. None is much bigger than the other, but I got locked out of it. So, okay, for a derivative function, this will be a positive slope. Similarly, you calculate, you will get for a 0.1k itself, you will get minus 20. For
Ma'am,
1k, yeah.
uh, you started. We can't see previous lectures also.
Oh, oh, until when you can see?
Only Bode plot definition you are telling that part.
Oh, after that itself, it went away.
Yes, ma'am.
Oh, God. Okay, fine. I've been teaching a lot after that. Did you see this?
No, ma'am.
This also.
Only yes, only first line that red color. Then all stop.
Okay, fine. I think there is some issue here in the IITM Wi-Fi thing, so I will explain it here. Okay. Fine. Now, in Bode plot is another kind of plot from the Nyquist plot where it we represent it in terms of log magnitudes. It will be easy for higher dimensional system to represent. It's a another type of tool we use. And from Nyquist plot, we need both magnitude and phase, but in Bode plot, we can use it, split it into a magnitude and phase. Either you can only calculate magnitude, otherwise only calculate phase. That sufficiency and customizable feature is there, and also you can compare one with another. And there are few things you need to learn before doing Bode for an entire transfer function. There are different types of transfer functions, starting with the lowest possible form, that is only the gain k. The next thing is k by s kind of term. So k by s or k by s power n, that is like 1 by s square, 1 by s cube terms. And derivative factor, that is if the s is in the numerator, one s by 1 or s by 2 kind of thing. Only 0 that is at the origin, that kind of system. And there are first order system, 1 by s plus t, 1 by s plus t the whole square kind of. And first order numerator, that is s plus a or 1 by st in the numerator. So we will see how to plot Bode plot for each and every system initially. Then if I combine two or three, then you will be able to plot the Bode plot easily. Okay, the first thing is constant gain. If I like, if something is not audible in between, just let me know.
Yes, ma'am.
Ah,
Now
okay, okay. Wait, I will join from control ID also. Okay. Okay. Now, for a constant gain. So how will I write for a constant gain? Another thing is, since I tell the Bode plot is in logarithmic scale, you always multiply whatever you do for a Nyquist plot with log of g of j omega. Whatever magnitude you find for Nyquist plot will be multiplied with log. And also in logarithm scale, we use decibels format. Decibel is our unit. So decibel in the sense 20 into logarithmic scale of whatever magnitude we used to call. So always this will be 20 log of magnitude, 20 log of magnitude. So your normal magnitude becomes 20 log of magnitude. So for general, what is the magnitude of k? Magnitude of k can be represented like this. For a Bode plot magnitude, it will be 20 log of k. That's it. So that I written it here. 20 log of k for magnitude. So now I changed one by one and told you how changing k will affect this Bode magnitude plot. For example, if I put k equal to 1, how this will become 20 log of 1. Log 1 equal to 0, so 20 into 0 0. So your plot will be here. Your magnitude plot will be at 0 decibels, right? When k equal to 1. What if I increase the k equal to 2, then log 2 will be positive. So 20 into log 2, somewhere above. So k greater than 1 will be above positive values of decibels. Then k greater less than 1 will be below negative values of the decibels. So by changing k, you can go around up and down in the magnitude plot. For phase plot, it will be 0. There are no things to change the phase, so it will always remain at 0. Clear? Constant gain is clear?
Yes, ma'am. Clear.
Fine. The next thing is we are going to see the integral factor. This is where it gets little interesting. So how? I will erase all the things that I explained. I will do it again now. Okay, fine. The same magnitude plot. So now I'm going to calculate for K by S. K by S in the sense I'm going to put J omega in terms of S. So the overall magnitude will become 20 log of K by omega. So if I calculate the phase angle, it will be tan inverse of 1. It will become minus 90, right? For 1 by omega, the angle would be minus P. The angle will become minus 90. So now this is your angle, this is your magnitude at angle. So how the magnitude plot will look like? When I substitute, wait, so my magnitude is 20 log of K by omega. So if I substitute omega equal to 0.1 K, how it will become 20 log of K by 1.1 K, it will become 1 by 0.1. It is 20 log of 10, right? What is 20 log of 10? It is 1, right? Log 10 is equal to 1, I guess. So it will become 20 decibels. Similarly, when I keep omega equal to 1K, it will become 20 log of 0. Sorry, 20 log of 1, it will become 0 decibels. Similarly, omega equal to 10K. You can find 2K, 5K, anything. Just randomly I'm picking 10K to find the slope. That's it. So this will become 20 log of 0.1. What is 20 log of 0.1? It is minus 20 decibels. So when I choose my omega, this is omega, right? In Bode plot, both are omega. So when I choose my omega equal to 0.1 K, my decibel is 20 decibels. When I choose K omega equal to 1K, my decibel is 0. When I choose omega equal to 10K, my decibel is minus 20. So if I connect this dot, I will get a line that pass through this 20, 0, minus 20. And if you find omega equal to 20K, then it will become minus 40. So if I find a slope between this, that is dx by dy, we call this difference in between this scale is as decade or decade, whatever they used to call it. Because 10, it will be in a power of 10. So 10 years we call it as decade, right? Similarly, 10 power of anything we call it as decade. So the slope will be represented as for every decade, there will be a change of 20 decibels. So the overall slope will be 20 decibels per decade. Clear? Magnitude always stays at minus 90 degree. Constant for integral factor for systems that looks like K by S. Now, what if a system looks like K by S power 2 or K by S power N? So if it is S power 2, then how this will become 20 log of K by omega square? Then the degree would be minus 180 degree, because 1 by omega square, it will be minus 90, minus 90. It will be minus 180 degree. So this will become square. So this will become 0.1 into 0.1. It will become 0.01. Then this is 40 decibels. This is again 0. This is minus 40 decibels. So your slope keeps on changing based on the poles type number. That is, so your pole should be 20 into n decibels per decade. And your degree would be minus 90 into n degrees. So for s power n, this is minus 20 into n. For s square, this will be minus 40 decibel per decade. It's minus, okay, not plus, it's minus 20 decibels per decade. So for S square it will be minus 40, S cube it will be minus 60. Similarly it goes on. For S power n it will be minus 20 into n decibels per decade, minus 90 into n degrees of phase angle. Similarly, for a derivative factor, if you do that, you will interestingly find that the slope keeps on going up. That is, it varies at plus 20 decibels per decade. So, for k by s power n, it is minus 20 decibel into n decibels per decade. For k into s power n, it will be plus 20 into n decibels per decade. So for k by s square, what is the slope? Are you with me?
Yes, ma'am.
For k by s square, what is the slope?
Then when minus 40 dB,
Yeah, phase angle would be minus 90 into n. How much it is?
minus 180.
180. Fine. Into 2, that is minus 180. Similarly, for k power s power n, derivative factors, it will be minus plus 40 for k by s square. Plus 40 and it is 180.
Yes.
Okay, fine. Now, this is what I taught so far. And in the first order term, similarly, if you keep finding for a first order system, it will look like this. G of s would be 1 by st. Then g of j omega equal to 1 by 1 plus j omega t. Then if I find a magnitude, g of j omega, magnitude would be 1 by root of 1 square plus omega square t square at an angle minus tan inverse of omega t. So, if you find for this, we will find it in terms of two different criteria. So, how it will be? There are terms, additional term t here, right, which was not previously there. So, what if how we approximate it? We will try to approximate it around 1. What if omega t is very much less than 1? Because there is a 1 here. No, we compare both two terms. And what if the omega t is very much greater than 1? We'll approximate around it. When omega t is very much lesser than 1, then this will become 1 by 1 because this terms will become a negligible one. So we will discard that. So your magnitude will more or less looks like 1. So 20 log of 1 equal to 0. Similarly, if the omega term is very much bigger, it will become omega t. Root of and omega square t square will be gone. So 1 by omega t. Then how it will be? So if I put 20 log of 1 by omega t, I can also write it as minus 20 log of omega t, right? Because
Yes, ma'am.
in logarithmic scale you can put minus and take the inverse above. So this will become minus 20 log omega t. Your magnitude will become like this. So when omega equal to 1 by t, how it will become? 1 by t, 1 log 1 0. Omega equal to 10 by t, it will become log 10. It will be minus 20 decibels. Similarly, if you keep on increasing, it will go to 40, some 100 by t if I put. It will keep on going for every decade. So now, for the first sometimes, if I draw a magnitude plot for this, for sometimes until it reaches the cutoff frequency omega equal to 1 by t, it will be stable with a magnitude of 0 decibels. And after that, it keeps on going down. That is minus 20 decibels per decade. As here. From here, I found a slope, minus 20 decibels per decade. So the phase will also be like that. So the phase will cross at, if I find a phase angle, you would know. Since the interest of time, I'm leaving that. I'm straight away writing it. It will look like this. When omega equal to same angle, omega equal to 1 by t, where we found this cutoff frequency. This we call it as cutoff frequency. If when omega t is lesser or less than 1, it means omega less than or less than 1 by t, right? So 1 by t is your cutoff frequency. So here it will cross 45 degree. For some time it will be 1, and at some time it will become nearly to minus 90 degree. There will not be this much space. It is nearly to minus 90 degree. Similarly, for a system first order transfer function of 0 would be 1 by s plus t, right? So in Bode, if you find 1, you will be able to write other. So as we saw the before one, how this will look like. So it will become 0 for sometimes, and it keeps on increasing, and the phase plot will look like this. Similarly, at 0, it will be minus 45 degree when omega equal to, here actually it is for omega equal to 1 by 2. This is at a decibels, minus 20 decibels, plus 20 decibels per decade. And introduce same thing, 20 into n for 2 or 3 zeros. This is minus 20 into n for 2 or 3 poles. So this is how your Bode general term will look like. So practice this for problems like this 1 by 2t. Then find Bode plot for this. Find a magnitude curve, and if you find a magnitude, it will be 1 square plus 4 j omega. T is 1. So it's 2s. Let's take 2s. 1 by 1 plus 2s. Then how you will write? 1 by 1 plus 2 j omega. So this will become magnitude become 1 square plus 2 omega square. That is 4 omega square. Tan inverse of minus tan inverse of 2 omega it is. So based on omega, your Bode plot will vary. That's it. Since it is a 1 by t square, I'm sure that it will, for some omega equal to 1 by t, or omega equal to 0.5, that is 1 by t. T is 2, right? So it will be 0, and then it keeps on going from minus 20 decibels per decade, and your phase angle would look like this. Yeah.
Uh, where you find t? Yeah,
Here,
omega
2.
equal to 0.5.
Because st, right? 1 by 1 plus st.
Okay.
T is equal to 2. So omega equal to 1 by t. So
Okay,
omega
then
equal to
first
1
we
by
have to
2.5.
compare with the main equation.
Yeah.
Then we have to convert that.
Yes, yes, right. Find the magnitude and phase. From that, you will be able to write, draw this code.
Okay.
Okay. You want me to solve some problem, right?
Yes, ma'am. Yes, ma'am. If you can, then it will be very helpful to us.
Let me open it. Which week 6?
Ma'am, week 7, that is gain margin. Question number 6, there is gain margin and
Graded
phase.
assignment.
Yes, 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 ma'am.
Question number 6.
Graded assignment. Yeah, yeah. Week 7.
Week 7, 6. Okay. The unity feedback system has planned transfer function. That one.
Yes, yes, ma'am.
For k equal to 8, draw the Bode plot and compute the phase margin and gain. Okay.
Ma'am, this question is also incomplete in the question. What we will do and where we give the answer, there is no option of that.
Uh, Gain margin. Okay. Okay, okay. Yeah, it was not given properly, right? It's supposed to be a short answer, comprehension question.
Yes, ma'am. Yes, ma'am.
but they have given it like this. Okay, I will check with the team to make this mark 0.
Yes, ma'am. I can't able to do that question.
Okay. So, the question tells for a unity feedback system, something like this k into s plus 4 by s minus 1 into s minus 2. Okay. So, first, for a frequency response thing, try to rewrite it in terms of 1 by s plus t format. It will be easy for you to solve it. So, how can I write it? It will be 2k into e 1 by 4s plus 1. 4 will be outside, right? Divided by 2 will be outside. This will become minus 2. So, minus s plus 1 into minus s by 2 plus 1. Minus into minus plus it will be. So, if I multiply it with 2, if I multiply it with 2s minus, so it shouldn't be common for these two, right? Okay, wait. Instead of doing this, 1 minus s, I will take minus 1 here outside and 2 into 1 minus s by 2. So this will be right. Okay. So we multiply 2 inside 2. This will become minus 2, right? 2 plus s by 2.
Yes, ma'am.
Okay. Then this minus and minus will get cancelled. This minus and this minus will get cancelled. Then this will become 2k. 2, this 2 and this 2 and cancelling out. Okay. 2k into s by 4 plus 1 divided by 1 minus s 1 plus s by 4. 1 minus s into 1 minus s by 2. Okay, this is my system. Just rewritten form. Same system, g of s. So the next thing what we will do, we will substitute g of j omega in the system. 2k into 1 plus j omega by 4 divided by 1 minus j omega 1 minus j omega by 2. Fine. Now, you have to find the corner frequencies. The corner frequencies, how will you find? As we found before, you have to look for the 1 by st is the t format you have to look for. That's why we wrote it like that in the denominator. If you find that in terms of it, it will become, if this is s plus t, then this will become 1 by t into s plus 1, right? So t is the denominator one here. So this will become 1 by 1, and here 1 by t is 1 by 2, then t equal to 1 and t equal to 2 in the denominator. In the numerator 1 by 4, then t equal to 4 in the numerator. Clear? As this will become 1 by t. 1 by t is equal to 1 by 4. Then t equal to 4, right? So 1 by t equal to 1 by 2. Then t equal to 2 in the denominator and numerator.
Yes, ma'am.
So t equal to 1 comma 2 in the numerator. This is corner frequency we used to call. T equal to 4 in the, sorry, this is denominator. This is numerator. They have given to choose k equal to 8. This is given in the question. Now, for a Bode plot, the magnitude for only the constant gain is k only. Na? So the magnitude of g of j omega at only for this k alone, it is 20 log of 8. It will become something like this in 24 around it comes. Okay. So for 8, it will be 24. So for this, you need to find draw the Bode plot. Okay, we'll draw the Bode plot. For k equal to 8, this will become 16. If I put 8 here, it is 16. 1 plus j omega by 4 divided by minus j omega into minus j omega by 2. There are no other information. So first we need to find the Bode plot for this, and then we need to do this. Okay. For Bode plot, how will you do for this kind of systems? We found the corner frequencies for all these things. First, for the numerator term, 1 plus j omega by 4, the corner frequency. First, I'm writing a table to find it easily. Corner frequency, slope, change in slope. Okay. Particular slope, change in slope. To find from 1 to 1. Okay. If this is your numerator, for numerator, the corner frequency is 4. 4 is your corner frequency, and the slope will be 1 plus j omega by 4. We have known that if this 0 term is in the numerator, then it has a slope of 0 for some time until it reaches 4 omega equal to 4, and it takes 20 decibels per decade, right? From here. First order system, that is in numerator. It will become 0 until it reaches omega equal to 1 by t, and it takes 20 decibels per decade. So this is 20 decibels per decade. The next term, that is in the denominator, this I am going to choose. For this, it will be 1 by j omega by 1. So for this, sorry, instead of writing this will become 1 by 1 minus j omega, right? So for this, the corner frequency is 1. Corner frequency is 1. For this kind of system, the slope will be minus 20 decibels per decade. Since it is in the denominator, that's a 20, and here it is minus 20, it will become change in slope become 0. Next, the next term I am going to take, this is 1 by 1 minus j omega by 2. So this will become 1 by 1 by 2, it will become 2. 2 is your corner frequency that we found already. So no need to confuse it here. Just 2 is your corner frequency. Then this again will take a minus 20 decibels per decade. Already 0, minus 20, minus 20 per decibels per decade. So this is your overall Bode's magnitude and
Ma'am, changing
stability.
why it is 20 minus 20?
Already 20 is there. There is a 20 slope, and then
Yes,
again minus 20. So 20 minus 20, it is 0. That is to continuously draw. So how to change,
yes,
how the Bode will change from 1 to 1. That is the
yes, ma'am.
simplest.
Yes, ma'am. Yes, ma'am.
Okay, fine. Now we found all these things. The other thing we want to found is to start from where. Since you have found the slope, you have to know where exactly it is going to start, right? So for this, you have to calculate this some omega equal to random omega, and at all the corner frequency, you should know where it is. 1, 4, 2, and 4, and everything. So For how will you find that?
Ma'am, we have to take 16 as amplitude, ma'am.
We
Will
have
you
to take
16 as amplitude? Um, we- will we have to consider that 16?
yeah, we have to actually 16. It's not 16, it is 20 log of 16. It's 20 log, right? It's in the decibel place.
Yes, yes, yes.
So it should be 20 log of 16. Give me a minute. Sorry. My screen is visible, right?
Yes, ma'am, visible.
One minute. Yeah, where I left, I said the 20 log of 16, right? You asked whether we have to calculate the
Yes,
16 log.
yes,
Oh,
ma'am.
fine. Before that, we will find the magnitude and phase calculation for this. Okay, paste, paste. No, fine. So K is 8, we know, so it will become 16 as it is. Now, I want to start with the constant gain, K, which is the easy way. That is, K itself is 16. 2 into 8, it is 16. We will calculate K as 16. So for this, we will calculate 20 log of 16. It will be around log 10 base of 16, how much it is. Some point something. Log 16. It's around 1.2 into 20. I will get around 24.08 around. So I'm keeping it as 24 decibels. Okay, constant gains we found. The frequencies in which we are going to calculate is 1, 2, and 4. So we will find slopes. We are already found slopes. That is from 0. From 0 we are going to start and we are going to follow minus 20. And one thing we made mistake here is we have to start from the lowest possible frequency, right? The Bode plot is like 1, 2, and 4. We started from 4 here, so that is a mistake. So we have to start from here, 1 only. So if it is 1, this will become minus 20. This is not 0, this is minus 20, minus 20 decibels per decade. And then from minus 20, and the next possible cutoff is 2. So this will become minus 20, again minus 20, it will become minus 40. And again you calculate this, if you calculate this fourth cutoff frequency, then it is plus 20, then minus 40 plus 20, it is minus 20. Okay, clear?
Yes, ma'am.
Just write it in terms of smallest possible corner frequency, that's it. So it will become 20 minus 20 minus 40 and 20. That's how the slope will be, right? So slope starts at 0 to minus 20 minus 40 and then it becomes 20 based on our cutoff frequency ranges. If the cutoff
And
of
then it
the
will be also minus 20.
what
Minus 20, minus 40, and then minus 20.
minus 20. Okay, okay, plus 20 is the individual scope. Minus,
Yes, ma'am.
yeah, right. So this is my slopes, right? Similarly, if I first of all I want to find the phase, how it will become 16 root of 1 plus omega square by 16 divided by, otherwise I'll write it simply, omega by 4 the whole square root of 1 plus omega square root of 1 plus omega by 2 the whole square. Right, this is my magnitude. When I calculate a phase plot, this will become for first one, already it is in a first order format, so it will become omega by 4 by 1. So it is omega by 4. Then minus it is minus tan inverse of omega. Already there is a minus here, so minus into minus plus. Tan inverse of minus theta is equal to minus tan theta, right? So sorry, tan of minus theta equal to minus tan theta. So it will become plus. There is a minus here also, so it will become minus of minus plus tan inverse of omega by 2. It is actually minus, but because it is in the denominator, but the term is not 1 plus st, it is 1 minus st, so we are multiplying again with minus. It's clear here, right?
Yes, ma'am. Clear.
It's not naturally plus.
Yeah, yeah, yeah.
Okay, fine. Now, when first we will test the limits when omega equal to 0, how this will become. When I put omega equal to 0, this will become 16 root of 1 divided by root 1 into root 1. It will become 16 only. When omega tends to infinity, this will become infinity, right?
Yes,
Simply
ma'am.
infinity by infinity it will be.
Yes, yes.
At a phase angle, when omega equal to 0, tan 0, 0, 0, 0. Uh, Angle will also be 0. At
0.
omega equal to infinity, this is infinity, infinity, infinity. Oh, sorry. 90, 90, 90, right?
Yes, ma'am. 90. Then
So it will
270
become
degree.
270 degree.
Yes, ma'am.
So your phase will starts from 0 to and goes till 270 degree. Now you have to find the magnitude at the cutoff frequencies. We know the cutoff frequencies 1, 2 and 4, right? So when omega equal to 1, your magnitude will become 16 root of 1 plus 1 by 4, 1 by 16 divided by root of 1, 2 root of 1 by 2 the whole square, 1 plus 1 by 4. So how to calculate this? 16 into root of,
Ma'am, we have to find individually for omega equal to 1, 2, and 4. All
yeah,
angle and magnitude.
yes, 5 by 4. So if I approximate it around 1, so it become, okay, some calculation will come. I will calculate it later. So when omega equal to 2, this will become root of 1 plus 2 by 16. It is 1 by 8 divided by 1, 2 square. It is root 5. This will become root 2, 1, root 2. Fine. This is around, if I calculate this, it's around what, 2.5. This is around 3.8 something around. When omega equal to 4, this is around, this is 16 root of 1 plus If I put 4 here, it will become 1, then it will become root 2. Root of 1 plus 4 square, 16, 17. Root of 1 plus 4 by 2, 2. 2 square, 4, 5.
5. Yes, ma'am. Root 5.
This will be around 2.3. Okay, fine. These are all some values you will get for at your crossover frequency.
Ma'am, for Bode plot, why we have to find these values? What?
So from Bode plot, if you find the Bode, like where it is crossing, when it is crossing the 0 decibels, the corresponding frequency, you will find the gain margin and phase margin. No? So when it is minus 180, the corresponding magnitude similar to minus 180 is your gain margin. The
Yes,
corresponding
yes, yes.
frequency at which your phase crossover, it is your phase margin. So plus 180 degrees your phase margin. So that's how you will find.
Yes, ma'am.
So your phase margin will be 180 degree plus at an angle where your gain crossover frequency is. So first you will find this gain crossover frequency from this and you will find that when it is crossing the one. So easily you can calculate. How you calculate is when the G of j omega is equal to 1, that's when you get this gain crossover frequency, right? So first you equate this to 1. Similarly, whenever we put this value 1, 2, 4, you will get something like 2.2 point, but it keeps decreasing, right? So you have to check with different values of omega. Otherwise, you have to equate it and find the value of omega. Maybe around value of 6, I'm getting something around gain margin. It is closely related to 1. So omega 6 is my omega equal to 6 is my omega GC.
Yes, yes, yes.
So whenever I have whatever value I get from omega equal to 6, that is my gain margin.
Okay.
Not like that. Wait. I confused it. Wait. So this is your omega GC. Your PM is equal to 180 degree plus phi of GC, right? Phase angle at GC.
Yes, yes.
So first you have to plot the phase angle. For each and every cutoff frequency, you have to plot the phase angle. So you have to find at omega equal to C, what is the phase angle here? Maybe around uh, 60 or something it will come. Okay, just find the tan inverse of 6. That's it. Here you put
Yes, yes.
omega. Okay. Where is your phase angle? Here. This is your phase angle, right? Put omega equal to 6. So this will become angle at which j omega of gc. That's what you need, right? So if
Yes,
I
ma'am.
put tan inverse of 6 by 4 plus tan inverse of 6 and what is next term? Omega by 2. Then plus tan inverse of 6 by 2. Then it will become tan inverse of 3 by 2 plus tan inverse of 6 plus tan inverse of
3.
3. So if you find value for this, you will get something around this is 55 plus tan inverse of 6 is 80. This is around 72. So if I add together, you will get something around 207 degree. So your phase margin is equal to 180 minus 207 degree. So it will become minus 29 or something.
Okay, ma'am.
27 something, right? So your phase margin is around 27 degree. So then comes the gain margin. How do you find gain margin? Gain margin is inverse of your gain value at phase crossover frequency.
Yes, ma'am.
So how do you find the phase crossover frequency? Phase crossover is whenever your angle G of j omega is equal to 180 or minus 180 degree.
Yes, ma'am.
So your angle value, you know, so you put something, you try with the um, your cutoff frequency and check whether it is decreasing or increasing. Then choose a omega where it similarly equal to 180. For me, it comes around 3.6 or 7, 3.7 degrees. When your omega is equal to 3.7 degrees, your overall angle is 180 degree. It is coming. So your phase crossover frequency is equal to 3.7. Just find your magnitude at 3.7. Put everywhere, wherever omega is there, put 3.7 and that's your gain margin.
Okay, ma'am.
It's little tedious problem, but by practice, I
Yes,
think you will be able to find it.
yes,
But
ma'am.
in exams, we won't ask this big question. We will give you the Bode plot and ask you to find from it. In Bode plot, it will be easy for you to find, right? Just trace around the minus 180 degree and gain margin equal to 1. You will find phase and gain crossover frequency. Along with that, you can find the gain margin and phase margin.
Okay, ma'am.
Okay. Thank you.
Okay, ma'am. Thank you.
More than one. Yeah. Bye.
Bye, ma'am. Bye.